All right. Hello. This is lectures being recorded for CJ 352, Forensic Science Lab 2. And this is within the STR lecture, if I haven't divided it up yet. But this is sort of its own little lecture about DNA and statistical calculation. And this relates to one of our assignments that we're going to do in the class where you're given a profile, 13 pairs of numbers from somebody, but we're going to keep it easy and give you like one pair of numbers or 5 pairs of numbers. And you calculate what is the frequency of that genotype. So to put it another way, you're going to calculate how many other people in the population walking around have the same profile as this evidence or this person. Okay, is it, because you can imagine an investigation, it's a lot different. If 1 in 10 people have that profile, then it could have been 90% of the population, or excuse me, 10% of the population. But if it's like 1 in 350 million, then that starts to give you an idea that, yeah, this DNA matches that individual and nobody else. So we're going to go through, because as we've discussed in 110, as we've discussed in this class, when a forensic scientist goes into court with DNA, they don't just get up there and say, it's his, high five the judge, and walk out of the room to cheers and applause. What they do is they actually describe to the jury what they did, tell the jury that the evidence matched the suspect, and then they have to give the jury some idea about the rarity of that evidence. And with DNA, it can actually be a statistical calculation. So what I want you to be able to do at the end of this lecture is to actually calculate the genotype frequency if you're giving a genotype at one locus. In other words, what is a genotype at one locus? Well, for DNA, it means, okay, at the locus D5S818, the person's genotype is 1314, 13 repeat and 14 repeat. Now, to be able to calculate that, you need some type of population data, and that's going to come in the form of an allele frequency table, okay? And we'll learn what that is, okay? Or you can calculate a genotype frequency when giving a genotype at multiple loci. So in other words, it's not just how many people have a 1314 at D5S818, it can be how many people have a 1314 at D5 and a 910 at TPOX and a 1415 at THO1. So you can be given multiple loci. And of course, in a forensic science lab, there's 13 pairs of numbers. And so we're going to learn how to calculate the overall profile when it's at more than one locus, okay? All right, so this chart sort of gives us an example of data we may receive, okay? So if we collect DNA from 5 different people, and we process their DNA with the primers for just D5S818, we get a pair of numbers, okay? So that pair of numbers is called their genotype. So a genotype consists of 2 alleles. Remember, 1 allele from your father, 1 allele from your mother. I'm trying to use the proper terminology here. So Wes is an 1112 at D5, Erica is at 1213, et cetera, et cetera. And then we'll notice, wait a second, DNA is supposed to be unique to an individual, but Rena is also an 1112. Is this possible? And the answer is yes, because we're just looking at 1. There's only so many numbers. Like at D5, everybody's probably going to be between like an 8 and a 14. There's only so many numbers that you can be. So obviously 2 people in a population, if you just look at one location, are going to have the same genotype, even though they're not related, they're not identical twins, okay? So we can calculate the frequency, how many people would match you or evidence at one locus, and then we're going to calculate how many people would match you at 13 loci. And obviously from this is a chart we saw here, it's nothing, it's just to remind us what those 13 loci are. Okay. So we can see that even though Wes and Rena match at one locus at D5, if we just look at 4 or 5 or 3, okay, as I mentioned in class, we're going to find that it's possible that 2 people could match at 5, but it's extremely rare. In other words, to put it in the terms of this lecture, the genotype frequency, or excuse me, the frequency of the genotype is much less, okay? So we're going to calculate the frequency. It's going to be a number, okay? And that number is going to get lower and lower and lower, okay? The number that we're going to calculate is actually a decimal point. So in other words, if 10% of the population match Wes at D5, if 10% of the population have an 11, 12, that's going to show up in our calculation as 0.10. Okay. So it's always going to be less than 1. It's going to be anywhere from 0.9, which it's not going to be 0.9. Okay. It's going to be like, we're going to get numbers like 0.1, 0.05. We're going to get numbers, because it's going to be so rare, like 0.0000000000098. Okay. And that's going to show up on your calculator in the scientific notation as like e to the negative something, like e to the negative 7. That means there's 7 zeros. We're not going to go over. And I will say this, when it comes to scientific notation, you can write down what you see in your calculator and you will get credit for it. Okay. You don't have to convert that. In other words, you're going to end up writing 0.00 number, 0.000 number. But once you get to like 5 zeros or 6 zeros, it's going to come up as scientific notation in your calculator. You just write down what your calculator says. Okay. All right. So the final results is not where the forensic scientist says the blood DNA in the blood stain is John Doe's DNA, and, you know, everybody cheers. It's going to say the estimated frequency at which this STR profile would occur in a given population is, and it's going to be a number. Okay. Now we're not going to convert our numbers to the 1 in 300 billion, but just know that 0.10 is 10%. That is 1 in 10. Okay. If it was 0.01, that is 1%. That would be 1 in 100. Okay. So 1 in 1,000. So it's sort of like the more zeros you have, or the more places after that decimal point you have, that 300 billion number just gets bigger and bigger. Okay. And 300 billion is sort of around the area of where we're going to be. We're actually probably going to be more in the trillions. Sometimes these calculations get in the quadrillions. And I can't even do it. It's like -12 to -15. So the scientific notation, that will not be uncommon. Okay. Now I can't remember. Maybe question number 10 may be written for our graduate level class. So you guys might get to question number 10 and I might just say skip it. We'll look at the assignment before we leave today. Okay. So that's an overview of what we're trying to accomplish. How do we do it? I want you to be able to calculate the genotype frequency. Okay, so this is an example of a question and the information that you guys would receive. Okay, I want you to calculate the genotype frequency at D5S818 when the genotype is 1113. Okay. Now, you may think, oh, I just go to the table and look up how frequent is 1113. But the way these tables are published, it actually requires you to do a little bit of math, because what's published is not the frequency of 1113. The frequency of the alleles are published. So that's why we call them allele frequency tables. Okay. So 11 occurs in 37% of the alleles, or 0.37 of the alleles are 11s. For 13, it's 0.19, okay, or 19% of the alleles are 13. Now, even though I'm not going to ask you a question about this, I think it's important to try to understand this. That allele frequency, it doesn't mean 37% of the population has an 11 allele. It means 37% of the alleles are 11. So if you picture it, okay, we're all sitting around and we have 2 ping pong balls that represent our 2 alleles, okay, and we write our genotype on there. So if I'm this person we're talking about, 11, 13, I would write an 11 on one ping pong ball and a 13 in another ping pong ball, okay, and everybody holds them up. Okay, that 37%, again, it's not 37% of the people who are holding up 11s. It's somebody goes around with a bucket and we all throw our ping pong balls in the bucket. Because you got to remember, one person may be holding up 2 11s, an 11 and 11. So that allele gets counted twice when it goes into the bucket. Plus, since everybody is holding up their alleles and throwing them in a bucket, when we total up all these numbers of all of the alleles, it's always going to total 100%. Okay. So again, that is 37% of the alleles that are out in a population are 11s. Okay, so hopefully that makes sense to you guys. If you have a question and can phrase it correctly, go ahead and throw it in the chat box there. Okay, so we can look up these numbers, okay? And here's an example, like at CSF, 7, 8, okay, it typically goes from 7 to 15, and if we add up these numbers, it might be 0.99, okay, but it should be very close to 100. And you'll also notice that there's zeros here, okay? That doesn't mean that 0 people have a 7 allele. It means that it's less than 0.01. Okay, and there are actually ways that forensic scientists can do the calculation if they do have an extremely rare allele, but we're not going to get into that. I'm not going to give you any zeros. I'm only going to give you numbers that where the allele actually has a number associated with it. Okay, so we got our first question. Daphne wants to know, how do they determine the frequency without knowing the DNA profile of the entire population? They estimate it, Daphne. So in other words, they have databases like right now, there's already millions of people in the DNA database. So they estimate the frequency based on the data that's currently in the database. And the more people they add, like, I mean, this is all population statistics, right? So eventually when you get like 10,000 people in the system, the percentage is not going to change as you add more people. Like 10,000 people sort of is a good representation of the population. And the percentages for those 10,000 are going to be the same as the percentages for 1 million people, because you randomly select the alleles, you know, even when you're up to 10,000. So it doesn't change that much. There is sort of a certain threshold that you'll need to reach in order to estimate the population, but we're already there for the most part. Okay. Now, you'll notice that profile said from a let's go back here. The STR profile would occur in a given population, okay? What that means, this given population, that essentially means race. And we're not going to, I'm just going to give you one population database, because you can do this just with all of the, people in the United States. But what happens is, especially if you're dealing with either paternity or partial profiles, what will happen is, my profile, because I'm a Caucasian, my profile is going to be more frequent in a Caucasian population as opposed to the general population, okay? Now, the actual difference is going to be negligible, or is not going to mean much in court. It would be where if you compare my DNA profile, the 13 pairs of numbers, the frequency of Dr. Linville's DNA is 1 in 350 trillion, okay? And then if I compared it to just a Caucasian, I forget, let's say that was 1 in 350 was for all population. If I just compared it to Caucasians, it may come down a little bit. It's 1 in 35 trillion. Well, that still means the DNA came from me and no other person. It came from me and no other person. It came from me and no other Caucasian person. But you always want to give the person the benefit of the doubt by comparing it to a database of individuals who are genetically similar to that person. Okay. So in other words, it can be like there are certain ethnic groups that are maybe indigenous to an island where you may need to recalculate the population frequency for those individuals because it's less frequent than if you just compared it to a database that you already had on file. But at this point, we pretty much have enough DNA data for all the humans on Earth that the numbers are pretty good. Okay. All right, so we have all of these numbers here that we can look up. All right, now we're going to go over the process that I want you guys to use. Okay, so now finally into the lecture, we're learning how to calculate the frequency. Okay, what is the genotype frequency at D5S818? The first thing I want you to do is go and find the genotype, or excuse me, the allele frequency for 11 in the tables. Okay, so 411 at D5S818 is 0.37. Got it. 0.37 goes right here, okay? You're going to multiply that by the allele frequency of the other number, 13, okay? Go back, 13, okay, that is 0.19. Where's my laser pointer? All the way up there for some reason. Whoop, okay? So that goes right there. Okay, so this is the first thing that you do. Find the allele frequencies for the numbers that you have, okay, and multiply them together. If yours was 1111, okay, then you would write 0.37 times 0.37, okay? It would just go twice, okay? It saves you half the work, okay? So that's the first thing. Find the two allele frequencies, multiply them together. The next thing you do is you need to ask yourself the question, is 11 the same as 13, yes or no? Okay, is 11 the same as 13? All right, I'm going to let you guys answer that in the chat box. Is 11 the same as the number 13, yes or no? I'm actually just thirsty and want to make sure somebody's paying attention. No, you guys are correct. So since they're different, we're going to multiply this by 2, okay? If they were the same, if it was an 1111, then we would not multiply them by 2. And that's what this down here means. This PP, it just means you don't multiply it by 2. They're the same. This PQ means you do multiply them by 2. They're different. Okay, now I'm going to say this once. Okay, it's not whether 0.37 is the same as 19, because it may be where the frequency of 11 is 0.25 and the frequency of 13 is 0.25. Okay. But it's not if the allele frequencies are the same, it's whether the alleles are the same. So make sure you're looking at the alleles when you're asking that yes or no question. Now, the reason for that is if they're the same, if you're dealing with an 1111, then you got an 11 from your mother and 11 from your father, right? Okay. Okay. And Rebecca asked, why do we multiply them by 2? Excellent question. And that's what I'm answering right now. If it's a 1313, you got the 13 from your father and the 13 from your mother, right? 1313. If it's 1113, there's 2 ways to get there. This is why we multiply by 2. You could have gotten an 11 from your father and a 13 from your mother, or you could have gotten a 13 from your father or an 11 from your mother, okay? It's sort of like, oh, remember this thing? Remember the pea pods, okay? You had your big A, it was one of the squares. You had your little a, that was one of the squares. But the hybrid, the big A, little a, okay, that was 2 squares, okay? You had to multiply that by 2. It's the same thing here. Because you can flip those, because there's 2 ways for you to get that 1113, you need to multiply that number by 2. All right, good. All right, so they're different, so we multiply it by 2. This, you don't have to do my hand, put it into your calculator, and you should get 0.14. And like I said, at one at one locus, that number is usually around 10%. Okay, I mean, sometimes it's 25%, sometimes it's 5, but in general, it's around 10%. In general, the decimal point is right here. All right. Okay, so that's your answer, okay? Look up the allele frequencies. Are the alleles the same, yes or no? If no, then multiply by 2. If yes, then don't multiply by 2. And then you write down the number. That's it, okay? All right, now, what if we have 3? What if I say, what is the genotype frequency at D5? I give you 2 numbers at, what is it? Here, my chat box. At D8, I give you 2 numbers, and at D18, I give you 2 numbers. You do exactly what we did, okay, 3 times, okay, and you can see around 10%, around 10%. This is a rare profile, so you may get a very small number like that. That's fine, okay. But if I want to know how many people are walking around matching at all 3 of those, we can use the product rule since they're inherited independently. Who cares what that means? But for you guys, the homework problem, the quiz problems, the exam problems, you multiply these together. You don't add them together, you multiply them. So look at what happens here, okay? If these were all around 10%, 0.1, 0.10, and 0.10, then if you had 1, it's like 1 in 10. If you had 2, 0.1 times 0.1 is 0.01. It's 1 in 100. If you have 3 loci, then it's 0.001. That's 1 in 1,000. So you can see that every time you add a locus, this decimal point moves farther and farther over. So that's why if you multiply 5 together, you may have like 4 or 5 or 6 zeros here. If you multiply like 8 together, you're going to have like 7 or 8 or 9 or maybe 10 zeros there. So the decimal point, as you add more locus, it should move over more and more, okay? So you always want to make sure if you have two numbers and you're doing the calculation and you wind up with a number that's bigger than those two, you've probably done something wrong. You maybe added when you should have multiplied. Make sure that these numbers are small, and the more loci you have, the smaller number that should be, the more zeros you should have. Okay, so this is a product rule. All right, does that make sense to everybody? Okay, what we're going to do now, I'm going to keep the recording rolling. I am going to do a new share, and I am going to share this. And I'm going to ask for your guys' help right now. Okay, right now, did the screen switch? Can you guys now see the PDF of the assignment? We're looking at a table with Wes. Okay, great. Thank you very much. Okay, so we're going to do this as a group. All right, and you guys, you'll have to move your chat boxes around. Like, let me shrink this up. Okay. Let me get my group chat out of the way. Okay. Down so I can see. We don't care about Erica, Jeremy, and Lori and Rena. We're just going to look at Wes. Okay. So down here, I'm asking, what is Wes's genotype frequency at D5S818? Okay, everybody. So what I do right now is, let me make sure. Oh, wait, I don't have a pen. Hold on. I need some type of annotation tool. Give me a, I know you guys can't see what I'm doing here. This, is that going to be, is the squiggly line? There we go. Okay. So down here, I'm going to write down, okay, Wes's genotype is 11 and 12. Okay. Now, wait, you guys can't, I'm trying to think, you guys can't do this unless you have it in front of you. All right. So this is going to be really sloppy. Okay. So everybody remember, write it down on a piece of paper in front of you, 11 and 12, so we don't forget, at D5S818. Then we're going to go down here to our tables. Oh, cool. The annotation stays right there. Okay. And I need to find my D5S818 on the table. Oh, there it is. Perfect. I'm not blocking it with the chat box or anything. Okay. And I can write down, and go back to the annotation here. Okay, for 11, let's see here, it is 0.37. Okay, does everybody see that? All right, and in the chat box, tell me, what is the genotype, or excuse me, the allele frequency at 12? Okay, what is the allele frequency at 12? I have 0.37, and I need to multiply this by what, 0.35? Yeah, that's right there. This is like Blue's Clues. I don't know. Is this what they do in that? Okay. All right. Now, come on, guys. This is tough. Is the number 11 different from the number 12? Yes or no? Yes, they are different. Or wait, what did I ask you before? If they were the same or something? Okay. Because they're different, what does that mean? Do we have to multiply by 2? Tabby got it in there. Yes, that means we got to multiply by 2. All right. Somebody, do you guys have a calculator or something? Let's do 0.37 times 0.35 times 2. I'm going to get out my little phone here. Can you believe this? All these things this phone can do, it also has a calculator built in. Okay. And then we'll see who gets it first. Okay. I got 0.259. Oh boy, I hope I get that number. I'm going to feel silly if I don't. Times 2. Hey, I got the same thing. Everybody agrees. 0.259. Okay. All right. You guys got this. Get rid of this. Okay. Then for number 2, okay, you're going to do the same thing, but at D7820. And then notice at number 3, where it asks you at D5 and D7, okay, you don't really have to do any math. You just take your answer for number 1 and multiply it by the answer for number 2. But please get in the habit of, don't just write the answer down under number 3. Actually write down the answer for number 1, rewrite it down here under number 3. Okay. Where am I at here too? Like, rewrite your answer 0.259 down here, and then show me what you're multiplying it by. Okay. Your answer for number 2. I want to see the work, because if you do something dumb on the quiz or exam, you can get partial credit by me seeing that, oh, you were doing it right, you just copied the wrong number, okay? Or, oh, well, where did that number come from? When they went to the allele frequency table, they were looking not at D5, they were looking at TPOX, you know. I can sort of track down the mistake you made, and it makes it easier on me. Okay, so for this assignment, what do we do? I think the Canvas is correct. You print out that PDF, this PDF, handwrite your answers in there, and then just take a picture of your answers and submit that through Canvas. Can I do ad? I can't do ads. Tiny Scanner, I think. I was on Android and I used an app called Tiny Scanner. It was great. On iPhone, I'm using Genius Scan, and that works really well as far as taking photos and converting them into PDFs. And then I don't know, but even if you just submit a picture, that's fine. All right, everybody. Does anybody have any questions about the assignment or how to do the assignment? Oh man, yeah. Okay. Yeah. So if you have an iPad and a iPencil or a normal pen, hey, Elise, do you have like the Apple Pencil, or do you have like just another pencil that goes with it, or do you use your finger? It's really like taking notations on that. Like I've been envious of students with iPads that just sort of like can take notes on it and stuff. And I'm like, man, I need one of those things. Okay, just a regular stylus, but it still works pretty good, right? I remember back in the day, like the styluses, they were like gigantic and it was really tough to write. Ooh, nice. Wait, fiber tipped. What does that mean? Is it like fat, or it's just like really like sort of tiny as opposed to the big, the bulbous rubber ones. That's the one that I'm thinking of. All right. All right. That's it. Do you guys have any questions? So did we finish early today? Did I fulfill my promise? Yeah, sort of. 2 o'clock. But at this point, if you're watching the lecture, hopefully you got enough. The quiz, no. So Rachel asked if the quiz is going to be multiple choice. The quiz, it's going to be short answer. Okay. Originally, I don't know, because it's a matter of what's going to be easiest for you, what's going to be easiest for me, and what is going to produce the most amount of busy work for a work study student, so we can still find an excuse to pay the work study student instead of not paying the work study student. Okay, does that make any sense? Like I have sorry, my brain stuttered. I'm like, wait, Rachel. No, wait, Rachel just asked the question. Rachel's not the student. No, Rachel is the person who asked the question and the student who's doing a graduate student who's doing busy work. We have a work study student, and I think I'm going to have Rachel. This is a long answer. I think I'm going to have Rachel actually take my question bank, because I didn't want to do it, and convert that into Canvas. So I think your quizzes will be where you sit down and you go through Canvas, but there will be some multiple choice, but there will also be some short answer as well. So you'll type in your short answer. But I'm going to give you guys a long time limit. Like I mentioned before, the quizzes are going to be open notes, but it helps to have your notes organized if you're going to do it that way. Also, I'll be making sure you phrase correctly. Excuse me. So for some of the answers, you can just copy down the answer that's obvious there in your notes, but for some of them, you're going to need to describe a step the way that we described it in class. And then obviously for these calculations, you're just going to do it. Excuse me. Yeah, because the other thing, what I might do, so Tabby asked if we can just do short answer and submit a picture. The other thing that I might do is, if it's annoying for you guys to sit and type, I might also include the PDF of the quiz. God, that might be tough. Actually, I think if the quiz is in Canvas, you can print it, or I can have the option of printing out the quiz. And so if you guys want to print it, it's not going to be pretty. It like might take for 15 questions, like 5 pages, because the spacing might be horrendous. But if you guys want to print something out and write your answers, or even if you just want to read through the questions, write your answers on a piece of paper and email it to me, I'm going to be very flexible as far as how you guys get it in there. But at this point, as of today, I think what I'm going to do for the quizzes is they're going to be in Canvas, and I'm going to have Rachel enter all of the quizzes from my question bank into Canvas. And then I'll just go through and select some, and it'll be the same type of questions that you guys have, but it'll just be in Canvas form. If that falls through, like if we can't get the images to work out okay, then it will be, me just emailing or posting the PDF of the quiz for everybody. You print it out, write your answers on it, and submit pictures of it. No, not you, Rachel. The other Rachel. Yeah. Yeah, your name is close enough, Rachel. I'm volunteering you to do work. Graduate Rachel Hensley. Yeah. Which I need to send Rachel an email. Okay, those are good questions. You guys have any other questions? We're going to meet on Wednesday. We're going to fill out a worksheet as a class, and I don't know how I'm going to do this with pictures or fake items. Like, I don't know, do I have a carrot that's shaped like a pipette? Maybe I can put Ronan on building me a Lego pipette. So we might do that as a project. And then I'll talk you guys through that lab on Wednesday. And then, wait, is the quiz on Friday? I don't know. Oh, hey, let me stop the recording here.